morning, class.
Good morning.
So, how are you today? Do you remember our lecture last time?
Yes, it is.
Joseph, do you remember? What was our topic last time?
Our topic last time is all about Phytagorean theorem.
Yes, last time we discussed the Pythagorean theorem. We discussed the geometric aspects of the Pythagorean theorem. And we also talked about the influence of a Pythagorean theorem on human civilization. So the Pythagorean theorem was really motivated by very practical considerations. But we can look at the Pythagorean theorem purely mathematically. It's just an equation having some solutions. So today I will talk about Diophantine equations, of which the Pythagorean theorem is one example. It's probably the most famous example. And I will show you the outline of my talk. So at first let's go back to the notion of the greatest common divisor of two integers. Do you remember what we mean by a greatest common divisor? Danica. Greatest common divisor or greatest common factor, the GCF. Sometimes it's called the GCF, sometimes it's called the GCD. For example, if we have two numbers, 10 and 21, what is the greatest common divisor of 10 and 21? 1. What is the greatest common divisor of 30 and 18? 6. So what are the factors? What are the factors or divisors of 18?
1, 2, 3, 6.
1, 2, 3, 6. No? So if we look at 18, 1, 2, 3, 6, 9, 18. No? 1 times 18, 2 times 9, 3 times 6. How about 21? This is 1, 3, 7, 21. No? So the common factors, what are the common factors of 18 and 21? We have 1 and 1. We have 3 and 3. So the greatest common factor or the greatest common divisor is just the greatest among all the common divisors. So we write GCD of 18 and 21 is equal to 3. Do you remember in grade school, how do we compute the GCD of two numbers? By listing, yes. How do we compute the GCD? For example, what is the GCD of 56 and let's say 27? So we list down all the factors of 56, and this is 1, 2, 4, 7, 8, 14, 28, 56. How about 27? We have 1, 3, 9, 27. Again, the GCD in this case, in fact, there is only one common divisor, and that is the number 1. So the GCD of 56 and 27 is 1. Do you know what we call those pairs of numbers having GCD equal to 1? We say that they are relatively prime. It means that those two numbers do not share a factor except 1. Of course, all numbers are divisible by 1. So 1 is always a common factor. But whenever there's no other common factor other than 1, then we say that those two integers are relatively prime. So I'll just write down the word relatively prime. So 56 and 27 are relatively prime. However, 18 and 21 are not relatively prime. Now, this is what we call the naive way of computing the GCD. Because it is very natural. We just list all the common divisors. Now, it becomes a problem when your numbers are very big. When your numbers are very big, then you have to guess what the factors are. And the bigger the numbers are, the more difficult it is to compute the factors. So we need a very special technique in getting the GCD. And this technique was provided by the Greeks. It is called the Euclidean algorithm. And I will teach you the Euclidean algorithm. Again, the concept of GCD is very important for the study of numbers and their equations. This is why I'm beginning this lesson by talking about the GCD. So when we divide two numbers, let's say, let's divide 35, let's divide it by, let's say, 6. What do? 35, how many 6's are in 35?
5.
There are 5 6's. So 6 times 5 plus? Plus 5. This is what we call the quotient. And this is what we call the remainder. This is what we call the remainder. Let's do another division. Let's say 72. Let's divide 72 by 5. 5 times, how many 5's can we find in 72? This is 14. 2 is the remainder. So this is the quotient. 14 is the quotient and 2 is the remainder. How about 72 divided by 6?
That's 12.
72, 6 times 12 plus 0. Whenever the remainder is 0, it means that 72 is a multiple of 6. Another way of saying that, 6 is a factor of 72, or 6 is a divisor of 72. So whenever the remainder is 0, then you have a complete division. Okay? Now, this way of writing a number in terms of its divisor, its quotient, and remainder is very important. I shall now discuss how we can efficiently compute the GCD of any two numbers. Now, let us compute the GCD of 56 and 27 without getting all the factors. Okay? So we want the GCD of 56 and 27. This is how we do it. We divide the bigger number by the smaller number. Okay? 56 divided by 27. We should get a quotient and a remainder.
That's 2. Remainder
2, remainder 2. Okay? Now we repeat it, but this time the divisor will become our dividend. I shall bring this down. This is 27. And then the remainder I will bring down as a divisor. So this is 2 times 13 plus 1. Okay? Now I repeat it. We will keep on repeating this process until we get a remainder that is equal to 0. So 2, right? And then the remainder we use as a divisor. 1 times 2 is equal to 0. Then the process stops. The GCD is always the last non-zero remainder. The GCD is the last non-zero remainder. In other words, the GCD is 1. Okay. This process of getting the GCD is called the Euclidean algorithm. It was introduced by Euclid, and it is very efficient because we do not have to compute the factors of two numbers. Also, it is probably the algorithm or the method that is being used in a lot of computer programs whenever the GCD needs to be computed. Okay? Let's look at another example. Now let us use the Euclidean algorithm to get the GCD of 234 and 56. Can I call on one of you? Jennifer, you'd like to try? So first step, we divide the bigger number by the smaller number. 234 is equal to 56 times a quotient. That was fast. 56 times 4 is 56 times 4 is 224, so the remainder is 10. Now you bring down the divisor 56 and divide that by the previous remainder, plus 6, and then we repeat. 10 is equal to 6.
4 is 6 equal to 4 times 1 plus 2.
Plus 2.
4 is equal to 2 times 2 plus 0.
Okay. So now we have reached a remainder equal to 0, which means again that the GCD is the last non-zero remainder. So the GCD of 56, that is 234 plus 56 is equal to 2. So this is again, this is the Euclidean algorithm. So if you have really big numbers, there's no need to get the factors because that is very difficult. But we can perform division. We can do that by hand. And the process stops in a few steps. Okay? Now, I want to talk about linear Diophantine equations. And in fact, again, I want to begin by talking about Diophantine equations. The term Diophantine equation comes from the name Diophantus. He was a Greek mathematician who lived around 200 AD. He was really interested in looking at the integer solutions of equations. So any equation can be seen as a Diophantine equation, but if we want instead of looking at all the possible solutions, we just want the solutions that are composed of integers. I'll give you some problems that you can reflect on. I'll start with a very practical problem. For example, in how many ways can a debt of, let's say, 65 pesos be paid in 10 peso and 5 peso coins? Of course, 65 is very small. One way of paying it is if we have 6 tenths and 1 5. Or we can have 0 tens, no tens, but we can pay it purely in 5 peso coins. So we have 13 coins. And of course, we can of course express this algebraically. Can you think of the equation? Yes, Alvin.
That's 65 is equal to 10x plus 5y.
10x plus 5y, 65. No? So 10x plus 5y is equal to 65. This is an example of a Diophantine equation. So we have coefficients of x, coefficients of y, and a constant term. The question here is that how many integer solutions there are. Of course, we want our x and y to be integers, no? Because x and y are just the number of coins with which we pay the debt. Okay? If we do not require this to be integers, for example, if we allow x and y to be real numbers, then we have infinitely many. This is just the equation of a line, right? Yes. Yeah. So think of the solutions like this. If you imagine the line on the xy plane represented by this equation, the solutions we want are those points that are purely integral in coordinates. All those real number ordered pairs which are integers. So this is one example of a Diophantine equation. I'll give you another Diophantine equation, this time asked by the Greeks. The Greeks, of course, wanted solutions to these equations. Another Diophantine equation. Can a perfect square be the sum of two perfect squares? Think about that question. It should be very familiar to you. Yes, Alvin?
It's just an expression of the Pythagorean theorem, which is c squared is equal to a squared plus b squared.
Yes, this is just the Pythagorean theorem. No? What we want is that can a perfect square be the sum of two other perfect squares? So what this question wants are solutions to the Pythagorean theorem. For example, 5 squared is equal to 3 squared plus 4 squared. So we say that 3, 4, 5 is a solution. I'll ask you another question. My third question. Is there a perfect cube that exceeds a perfect square by 2? Can you think of a perfect cube and a perfect square that are so close apart? Their difference is 2. Yes, Joseph?
2 and 4.
2 and 4. Well,
2 is equal to 8.
yeah.
The square of 4 is equal to 16.
Yes. Okay. But when we say exceeds by, we are looking at the difference.
Perfect square and a perfect cube.
Perfect cube and a perfect cube. Yes, Edu.
So, perfect cube is 27 and the perfect square is 25.
Yes, 27 and 25. With this question, what we want are solutions. Y squared is equal to x cubed minus 2. So one possible solution is one solution. X is 3, y is 5. Another solution is x is 3, y is negative 5. Right? So now we have two solutions. The question, are there other solutions? This is a very old question, but somewhere in the 18th century, it was shown using imaginary numbers that there are no other solutions. In my third lecture, I will talk about Euler. Showed that 3, 5, and 3, negative 5 are the only solutions. And what is amazing is that he introduced the use of imaginary numbers. So this is a very classic equation, a very classic question that was asked by the Greeks. And it took a long time before mathematicians could actually show that there are only actually two solutions. Okay. So now we talk about the simplest type of Diophantine equation. We call it the linear Diophantine equation. The linear Diophantine equation. Now the linear Diophantine equation has this form. A and B and C are integers, and we ask whether there are solutions to the equation ax plus by is equal to c. So by a solution, we mean a pair of numbers x, y. And we want x and y to be integers. For example, 10x plus 12y is equal to 99. This is a linear Diophantine equation. Do you think this is a solution?
No, there's no.
There's no solution. No? Because notice that whatever x we have, 10x would always be even, right? Whatever y we choose, 12y is always even. Even plus even is always even. It can never be odd. So we know that this is no solution. No solution. How about 3x plus, let's say, 5y is equal to 34. Can you think of a solution? 8
X is 8, y is 2.
and 2. Yeah, that's one solution. A solution is 8 and 2, right?
They're negatives. Negative 8, negative.
However, if these are negatives, this will become negative 34. Yes, Drexel?
X is equal to 3.
X
Y
is,
is equal to 5.
x is equal to 3, y is equal to 5. Yes. 3 and 5. 3 times 3 is 9. 5 times 5 is 25. 9 times 25 is 34. Can you think of a solution involving negative numbers? For example, if x is negative 2, then this should be 8. Yeah. 3 times negative 2 is negative 6. 8 times 5 is 40. 40 minus 6 is 34. No? Now, in fact, every time there is a solution, there are infinitely many solutions. We will never run out of solutions. But there are equations, Diophantine equations, that have no solutions. The rule is this. If you look at the Diophantine equation ax plus by is equal to c, you have to look at the GCD of a and b. We can compute that using the Euclidean algorithm. Okay? If the GCD is, if we call the GCD d, now next we check whether d is a factor of the constant term c. If d is not a divisor of c, then the equation has no solution. However, if it is a divisor of c, then there are infinitely many solutions. In fact, this we have a statement that says that every time we have one solution, if xy is one solution, then all other solutions are given by this formula. We can just replace t by any integer and we get infinitely many solutions. I'll give you an example. If we have something like, 7x plus 15, y 21x. Suppose we look at the Diophantine equation, 21x plus 18y, let's say, is equal to 29. Now, we know that the GCD of 21 and 18 is 3. But 3 is not a divisor. However, 3 is not a divisor of 29, therefore, we conclude that this linear Diophantine equation has no solution. No solution. However, we can look at equations like 3x plus 5y is equal to 34. What is the GCD of 3 and 5? 1. These two numbers are what we call relatively prime integers. And every time the GCD is 1, every time the coefficients of x and y are relatively prime, then we always have solutions, because 1 divides anything. So the GCD of 3 and 5 is 1. And therefore, 34 is divisible by 1, so there are infinitely many solutions. Okay? Now, let us illustrate this statement. How is it possible that all possible solutions can be obtained from just one solution? If we look at the linear Diophantine equation 3x plus 5y is equal to 34, the first solution we thought of was x is 8 and 8 and 2. Okay? Now, we want to form that. Let us, in this equation, our a is 3, our b is 5, and our c is 34. What is the d? This is the GCD of a and b. This is 1. Okay? So, our formula states that all possible solutions are given by, this is our big X and this is our big X and our big Y. All possible solutions are given by small x equal to our big X, 8 plus b over d. B over 1 is 5 t. Okay? And y is given by our big Y there, 2 minus a times t, so 3 t. This means that we can just replace t with any integer and we have all those solutions. So solutions, t, we have our x and our y. Okay. If t is 0, if t is 0,
8 and 2.
x is 8, y is 2. So 8 and 2 are solutions. How about if t is 1?
13 and negative 1.
8 plus 5 times 1 is 13.
Negative 1.
Y is equal to 2 minus 3 times 1 is negative 1. So 13 and negative 1. And you can check. 3 times 13 is 39,
Minus
plus 5 times minus 1 is
negative 5.
39 minus 5, and that's 34. So that's one solution. Let's look at bigger things. For example, t is 4.
8. Negative
8 plus negative 4, plus 5 times negative 4 is 8
8 plus 20.
plus 20.
28.
So this is 28. Y is equal to y minus 3 times 4.
Negative 10.
2 minus 12 is negative 10. 28 negative 10 gives us another solution. In fact, we can replace t with negative numbers. Let's say negative 2. If t is negative 2, we have 8 plus 5 times negative 2. That's 8 minus 10. This is negative 2. Y is equal to negative 3 times negative 2, positive 8. In fact, this is one of the solutions that we wrote down. You will see that from one solution, we can actually get all possible solutions. In fact, our solution does not have to be 8 and 2. We can choose any of these to be our initial solution. And using this formula, we can get all possible solutions. So if we go back to our original problem, in how many ways can a debt of 65 pesos be paid in 10 peso coins and 5 peso coins? This is a particular example of solutions that we're looking for. Of course, in that equation, we are looking for non-negative solutions. But when we say that there are infinitely many solutions, then it allows negative solutions. Okay? Anyway, this is the earliest type of Diophantine equation that was considered by the Greeks. And crucial here is the role of the GCD. Now let's go to our next Diophantine equation, which is the Phytagorean equation. Now let us have one exercise problem for solving Diophantine equations. Find, let's say, 5 different solutions. Let's say 4x plus 9y is equal to 24. Is this solvable? The GCD of 4 and 9 is 1. And 1 is a divisor of 24. Solvable. So remember that the first thing we have to do is to find one solution. If we get one solution, then we have infinitely many solutions. But first, let us identify the coefficients here. Our A is 4, our B is 9, our C is 24, and our D is 1. Can someone give me One solution? Yes, Alvin?
6, 0 is one solution.
6, 0 is one solution. No? Okay, one solution. Six, 0. Now, can you give me 5 different solutions using our formula? Maybe I can ask Sherilyn. Can I ask you to write the equations, the formula for x and y, and give us a table that will give us 5 different solutions of our Diophantine equation?
40 lang po.
96.
Minus 40.
40. Negative. Di ba? Negative 40.
Negative 40.
Negative 40.
Y
So,
equals to
Let us look at Sherilyn's solution. We want to solve this. We have one solution, 6, 0, and we use the formulas that we discussed. X is equal to the x coordinate of the first solution, which is 6, plus b over d, then that's 9 times t. And y is equal to
The first one is
0
minus.
minus a over d times t. So that's negative 0 minus 4t. So this is negative 4. Notice that every time we use a positive integer for t, our y would automatically be negative. So our first solution, our initial solution, was obtained with when t was equal to 0. If t is 0, then xy is just 6, negative 4. Oh, if t is 0, xy is just 6, 0. If t is 1, we have 6 plus 9, so that's 15.
50 times.
Negative 4 times 1 is negative 4. If t is 2, we have solutions 24, negative 8. If t is 3, we have this solution. For t is equal to 4, we have this solution. For t is equal to 5, we have a rather big solution, 51, negative 20. But all of those are solutions to our Diophantine equation. In fact, our initial solution, the first solution, can be any of these. We can choose any of that to give us our first solution. We will just have a different set of equations. But whatever initial solution we get, we shall be able to come out with infinitely many solutions. This technique was known to the Greeks. They were interested in methods of solving equations like this. Again, the main question that if you have a Diophantine equation, you have an equation, how do we find all the solutions? Another question, of course, the first question we have to ask is, are there solutions? And the Greeks found out that knowing the GCD of the coefficients a and b would tell them whether or not a linear Diophantine equation will have solutions. Do you have any questions about linear Diophantine equations? None. I hope this is clear to you and you remember that. Next we go to probably the most famous of all Diophantine equations. This was the equation considered by Pythagoras. The next Diophantine equation that we shall discuss is called the Pythagorean equation. X squared plus y squared is equal to z squared. So Diophantus and the Greeks are interested in the integer solutions of this equation. So they wanted to find out which integers x, y, and z would satisfy this equation. We call it the Pythagorean equation because this is the type of equation that Pythagoras associated with right triangles. Except that in the Pythagorean theorem, solutions to the Pythagorean equation can be any real number. any positive real number. But if we look at the equation as a Diophantine equation, we only want integer solutions. Now, of course, we have many solutions that we can remember. For example, 3, 4, 5.
6, 8.